Okay. All right, so first, any questions? So I started a screen recorder so that hopefully there'll be a YouTube version of what's on the screen along with audio afterwards. I typically do that when I'm teaching, but I had forgotten to do that the first 2 days of class. Sorry. Okay, so this is lecture 3. What we're going to talk about in our second day of the crash course on Python is control structures and functions. So control structures such as if, while, and functions, for, and functions which are defined using def. So really there's just 4 keywords. The syntax for using each of them looks very similar to the others, but there are numerous annoying subtleties and non-annoying subtleties involving them, which I'll mainly focus on. So first let's start with the control structures. Those are if, while, and for. And the way it works is you say if, and then you give an expression that evaluates either true or false. And then inside, then you give a colon, by the way, and then inside of that, indented at the same level, you give a bunch of code, which could be defining functions, could be doing all kinds of stuff. So this is many, many lines of code. But the key thing here is that it has to be indented. And it has to be systematically and uniformly indented. Because of this, if you're going to write Python code, you have to have indent. But when you write Python code, you have to have an editor that is capable of shifting blocks left and right easily. Like if you have some highlighted code, you have to know how to easily shift it to the left or the right. If your editor is not capable of easily doing that, then you should figure out how to, well, then you shouldn't be using that editor. Any decent editor should be able to shift code left and right. So then you have that, and then you can also have elif, and you can have a whole bunch of these elifs. So this is just like else if in any other language. And then finally you have an else. And I guess the main things to remember here are that after each expression you have to have this colon, which some languages you don't have that. So there's a colon, not braces, not begin ends, not no colon at all. There's a colon there. And it's also elif, not else if or something else. Any questions? Right? So here's a little example. So, what the heck? Just using this. Okay, good. All right, so let's try. So this is a little bit of code that illustrates a for loop, illustrates an if-else construction. So we'll set the variable b equals 17. The expression is b mod 2 equals 0 here. So if that's true, then it does this. Else if 2 equals 2 is true, then it does that, which is what it does. Else if nothing else caught it, then it does this. Okay. So let's see. If we want to make the first one happen, we would change this to a 1. And then you see that, in fact, that one's true. So only this code is evaluated. This code's completely ignored. And if we make both of them false, then the third one is good. One key point that I should emphasize is there's no switch or case type of construction in Python. So that is annoying, but it's the way it is. I think the idea is that because Python is an interpreted language, not a compiled language, you would really have no significant speed up by doing a switch and then having a big list. That said, I think code readability wise, it would be really nice if Python did have a sort of a case or a switch statement. I wish it did, but it doesn't. Sometimes you can do something very similar by making a dictionary with the code you want to evaluate in each of the cases or something, but Basically, it's not there, and what you end up doing is if something, elif something else, elif something else until you get the appropriate case. So don't go looking for this in Python. It's not there. Sorry. So that's one thing. Okay, so that's it. Any questions at all about the if statement? It's pretty straightforward in Python. Yeah. Actually, there's a big subtlety with the next one that I better remember to talk about. So for iteration, there's a for loop and a while loop, and there's no do or until. So you can't do something like do blah 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 until some condition is true. That just doesn't exist in Python. Python is easy to learn because there are less things to learn. But these are things that you can simulate using other instructions, like a while loop. You just do while true, do a bunch of stuff, and then check the condition and break at the end if you want. Okay, so the way the for loop works is you say for some variable name in something that's iterable. And in Python, there are many, many different types of objects that are iterable. But it's not like in C or other languages where you do for and then you have some variable that you explicitly vary over some range, checking a condition. Instead, what you do is you make some object that can be iterated over, and then you do for blah in that object, and it iterates over the object. This has some funny implications regarding memory, because the typical thing that your default instinct to iterate over is a range, which is something in Python that's the integers from 0 up to some number. And it literally constructs that range in memory. It constructs all those numbers, and then you iterate over them. And so if you say iterate over the numbers from 0 up to 10 to the 7, it happens to be extremely inefficient memory-wise. And so Python has some other construction called xrange, which you might not think to use because for small cases you never need to, which is a little bit better, and I'll illustrate that. In Python 3, this distinction disappears. Okay, so let me just show you for loops. So here's this little thing. So here's how you iterate over the numbers from 0 to 4. Ooh. I guess that's very unconvincing. So let me change it. So the numbers from 0 to 10. Okay, so it's simple as that. Parentheses are green, so you can barely see them. So what this does is it constructs this object, which is the integers from 0 up to, but not including 10. And let me show you how that looks. So it's just a list, and then it says for v in that list, and it makes v equal to each of the entries in that list. There's a subtlety here, though. What do you think v is right now? There are a couple of natural answers, and then we'll see what you would hope would be the case. One would be v is none. Another is v is undefined. It's just not defined at all. Another is that v is equal to 9. And another might be that v is 10. So that's at least 4 reasonable choices for v. Here's what Python chooses, 9. So what happens here is, as the loop is executed, v is set equal to each of the values in the loop, or each of the values in the iteratable, and when you exit the loop, it's just equal to the last value that you have there. It's pretty reasonable, because we're not checking a condition at each point. In C or some languages, you would do something like you'd set v equal to 0 and then v equal to 1, and at each point you'd check a condition. And then when you get to v equal to 10, the condition would not be satisfied, and you'd exit the loop. So that's why you'd end up with 10 in C versus 9 here. So watch out for that. But here's where the real subtle, or the really annoying subtlety is. If you do, say, v for v, actually let's say v squared for v in range 5. So we'll do a little list comprehension. In Sage, you can do a caret symbol for exponentiation, whereas in Python, it's exclusive OR. So since I'm kind of just talking about Python right now, I'll put that. Okay, so we do this, and we've made a list. What do you think v is now? Or actually, what are the possibilities for what v might be? Undefined would be ridiculous, given that v was already defined up here. It would really suck if doing a list comprehension suddenly undefined v. Another possibility is that v is still 9. And a third possibility is that v is 4.
Why would it be 9?
Well, because somehow maybe there's some scope in which this is evaluated, and the fact that we use the letter v here shouldn't count, shouldn't impact the global scope of the v. So those are just different possible choices people designing languages might choose. And I think in, well, I'll tell you what it is in Python. For. So here what happens is it's exactly as if you were to have evaluated the full for loop and made this list. As much as possible, list comprehensions always work that way in Python. Yes? You seem happy with this, right?
Yeah, fine.
Okay, good.
I just had a question. So, like,
Sure.
after the end, does that object have to be a list?
After the what? The end?
The word end?
It has to be something that can be iterated over. There's a ton of things. What?
Would a simple work, for example?
Yes, I think tuples can be iterated over. So let's try that. I mean, I know that they can. Anything for which there's any hope really to iterate over them is allowed. So yeah. You could even do, so in Sage, I defined, the prime numbers, an infinite set. So you can do that. I better do if p is greater than 10 break, otherwise it'll be a lot of pain. But so you can you can iterate any object that has some sort of iteration protocol. There's a way to when we get into classes more, we'll learn how to do this. But you can define a class, even an infinite, that represents to you in your head an infinite structure, and you can define a notion of iterating over it, and that's how you get this sort of thing. Okay. Oh, I just wanted to. See, I think I have Magma in here. I hope if I have Magma in here, we can see what Magma does in this case. Since Magma has, oh my god, what happened here? All right, looks like I might not have Magma installed here, based on that. Let me just, it would be really useful to, or at least, let me just see if I have Magma. Yeah, there's Magma right here. So Magma, another computer programming language with list comprehensions, maybe. Okay, so here in the Magma programming language, you have list comprehensions again. This is actually a sequence comprehension because in Magma, the square brackets notation is not a list, it's a sequence. But here, the variable that you use in defining the sequence doesn't bleed into the scope of your session. And I think it's also unaffected. So doing this, I think, it doesn't touch the variable. It doesn't matter what variable you use in there. In Magma, when you do a list comprehension, it doesn't impact the scope outside of that list comprehension. Whereas in Python, it does. Okay? So this is, in a sense, an arbitrary choice. And Python made one, and in Magma, it's a different one. So don't think that there's like necessarily a canonical choice. So you really need to just know these things. All right, here's an example of a while loop. So I'll make it a little bigger. I'll throw in a sleep so you can see it do its thing little by little. So what this does is it sets I equal to 0, and as long as I is less than 10, it increments I, and it's fine. And at some point, I wasn't less than 10, so terminated. What's the value of I right now? Is it 11? 10. Yeah. It's 10 because, I mean, if I put the print on the other side, then you would have guessed one more than what I printed. But it was when I equaled 10 that the condition failed, and then you immediately exited the loop. So I is 10 at that point in time. So notice it started at 1. I guess it would be funner to, it would be fairer somehow to put this the other way, given our previous discussion. Now I is 10. Okay, so that's for and while loops. can't really, specifically, I can't really think of anything else about them except there's a break statement, which you can use for both for and while loops, which inside of the body of the while or for loop, if you type break, then it brings you out of that. This gets you one level out of the for or while loop. If you somehow want to jump multiple levels out of some nested for or while loop, then you do not use a goto statement, because there is no goto statement in Python. What you do is you learn about functions, which is what we're going to learn about in a few minutes, and you write your code in such a way that instead of breaking out of multiple levels of a for or while loop, you return from a function. That's the right way of dealing with that sort of issue. Alternatively, you might have some logical condition that you test that makes it break multiple levels, but it's almost always best that if you have a nested for or while loop and you want to break all the way out, that you put everything inside of a function and then just return from that function. Okay, in case that isn't crystal clear to you, I mean something like the following. Well, let's see. Just make this really simple. J equals I while 10 J. Let's see, if J, what if you wanted to do something like if J equals I and I equals 7, I mean something kind of ridiculous like that. You want to break out of the whole thing. You cannot do that. You have to put all this code inside of a function and then return from the function. So super break. Nope, no such thing. So you can't just break out of all of the code. That's all I'm saying. Okay, so now the one other thing that, I mean, the real interesting aspect of, for example, the for loop is what you're iterating over. And here are some further remarks systematizing what I said before and adding a little to it. So there's the range function. This is a function that gives you back a list of ints. These are C ints, or they're Python objects that map to C, that correspond to C integers. And it literally constructs in memory, when you say range n, a whole bunch of objects, uses up a lot of memory. You can type range of 10 to the 9 and run out of memory on your computer pretty quickly when you do this. Actually, well, this is a bad idea, but I'm sure I'm going to regret this. There's a command in Sage, get memory usage, which just wraps something in. It's a surprisingly, oh, that's how much memory has been used in the current session. If I do v equals range 10 to the 7, then call this. I don't trust that. No, it's probably a very bad idea. It's probably sitting there swapping, and this is not good. This would be much funner to do if, instead of running on a little virtual machine on my laptop, this were running on a machine with a lot of memory. Of course, QuickTime's using an enormous amount of CPU resources. That sucks. Well, let's see if I've just killed everything. Yeah, of course I have. I should start bringing a bigger laptop too. Very bad idea. Of course, Apple's updating something that I didn't even open. Jeez, this is frustrating. Well, in any case, it's silly because if I want to iterate over the numbers up to 10 to the 8th, I don't want to use up a huge amount of memory. And that's where xrange comes in. It is a similar command that doesn't use up all of your available memory, like I've just done, causing the thing to start swapping like crazy and hence become completely inaccessible. That's not good. So I'm going to try to kill the using a lot of memory process running in this virtual machine on my laptop. Yep, see, swap. Okay, this shows you that a huge amount of RAM is being used. You see the swap daemon running and then Python using way too much memory. And now I've just
killed that Python process, and so now everything should be good to go again. So they'll probably have to restart this worksheet. Oops. Wow, it's really painful running this QuickTime player because it uses it's literally just using all CPU resources to record this. Looks obnoxious. Right. Okay, I guess it's all working again. But I've amply illustrated a problem that people often run into with Python, and which is fixed in Python 3 apparently. They just unified these two notions of range. And the fix in Python right now is xrange does is it gives you back an object that's just called xrange again, and that object can be iterated over, but it doesn't use an enormous amount of memory. I shall either horribly embarrass myself or illustrate that right now. So if the computer continues working even after I did this, that illustrates that it's not using an enormous amount of memory. Any questions? I didn't understand everything you just said, unfortunately. Yes. Oh, why there's no 10 at the end. So what the range never includes the endpoint. So this range command always goes up to, but doesn't include the endpoint. So what it does is it goes 1, 4, 7, and then the next one after that would be 10. And the range in Python goes up to, but does not include the top value. That's it's basically because of how people use range and the fact that Python is zero-based, all indexing is zero-based. It turns out that's always what you end up wanting. And if you write the range command where it includes the endpoint, things are often, you have to be a little bit more careful. In Sage, we did add an analog of range that does include the endpoint with some nice notation, which I'll show you in a second, but you'll run into this. But the issue is simply that range, if you just look at the documentation, it goes up to but does not include the top endpoint. The documentation should appear. Okay, so here it is. Return a list containing an arithmetic progression of integers that goes from I to j minus 1. And then there's an exclamation point emphasizing something, but range 4 returns 0 to 3. So this is another gotcha with Python you have to watch out for. Yes?
This might be a dumb question,
Mm-hmm.
but so if you're iterating over something and something's not ordered, like a set,
Yes.
right? Then does that, I mean, it seems like it's obviously better to iterate over a list because it's ordered. So is there the iterate method, I guess, for things that aren't ordered has to work harder, right?
It doesn't necessarily have to work harder, but it is a little more dangerous to use. But you're absolutely right. You can iterate over a set. The order in which the results appear is not, there's no guarantee on how it will appear. And so, for example, if I do for n in, and I define a set like 1, 6, 3, 8, 4, print n. On this computer, that's what I ended up getting, 8, 1, 3, 4, 6. Could very well get something completely different on a different computer or in a different session on the same computer. So it's not well defined, and that can cause a lot of trouble. But speed-wise, it's chosen some way of storing that stuff in memory, and it might very well be just as efficient as iterating over a list of the same elements.
Right, okay, so the reason I
Yeah.
was confused is just because when you had the prime set,
Yes.
then it was in order.
Yeah, I mean, the way it's implemented, I implemented the iterator. What you do is you just implement this method called underscore underscore iter underscore underscore. It's a method of the class.
You change it.
Yeah, and you get to decide on the order for your particular structure.
Okay, you just happened to decide
Yes.
that one.
Yeah, there's also an iterator on the rational numbers, which is kind of fun. Like, the rational numbers are countable. And there are many ways in which you can systematically enumerate the rational numbers. But some guy named Conway came up with an extremely efficient algorithm that will provably enumerate all the rational numbers without ever having to compute GCDs. Like, you know that each one you get is already in lowest terms. And so that's the one that Sage uses. So you can look in the source code if you want at that. I don't know if anyone has ever used it for anything in Sage, because why would you want to do for A in the rational numbers? But the rational numbers are an object, just like anything else in here, called QQ, rational field, and it has an iterator. Okay, a few other things. So there's an S range in Sage. If you try to do range, what it does is it just silently turns the inputs into integers by truncating them to, like, basically by rounding them down. That's what it does. It just, without any comment, turns them into ints and then computes the corresponding range. This might not be what you want. It's pretty hard to imagine it is what you want if you were to type that. So I wrote another range command for Sage called srange, and it does what you probably really wanted. Namely, it will really give you something that starts at that one, and by default the step size is 1, keeps increasing until it gets 2 but doesn't include the endpoint. There is an option to have it include the endpoint if you want, but it's not on by default. It's also nice because you can even give it symbolic input like pi and e, or I don't know, pi squared, for example, and e. You'll get a different list. And it iterates through symbolically and giving you back a bunch of symbolic objects. It really just takes the first object of any type at all, keeps adding until it hits until some comparison with the last one isn't satisfied. So you may need to use srange. S stands for Sage in this case. There's also an A range in the NumPy library. NumPy is a numerical Python computing library. The A range command is supposed to be very much like the kind of analog of the range command in MATLAB, in that it always gives you, no matter what you give it, it gives you back floating point values spaced in a sensible way, and it has various defaults and options that you can pass it. Okay, so there's all this, and I don't have them in the slides yet, but I'll just show you. There's a couple of other things that are Sage specific. So I'll just note that, Sage specific. So these were implemented by Robert Bradshaw, and there was a Python enhancement proposal, a PEP, to implement these in Python, which was rejected from Python. So he implemented them in Sage. So they're available in Sage. And what they do is they're kind of like what you'd see in some other, like in MATLAB or Maple or something. You can do square brackets and then give some lower bound, dot, dot, and then an upper bound, and it will give you the range inclusive of the endpoints. In math, this is often useful. Yes?
Are there ways to make these increase by another algorithm?
That's a great idea, or a great question. Yes, you can do, if you just give a second value, like 1.5, then it will figure out the arithmetic progression, and there you are. So you just give the first value, comma, the second value, comma, dot, dot, in the end. And it will give you that arithmetic progression. And it will work with, like you could, what? Yeah, well, it should go by a half, because it just figures out the arithmetic progression.
And in the Sage specific one, you just add the step on the end.
Yes, this would be completely the same as, and under the hood it probably just calls srange with a step size of 0.5, like that. Okay, so that's, and again, you could put like pi here if you wanted, for example, and it'll do something intelligent. I guess there's not very many, but if I put 10 here, there. Okay. And then there's also a version that's like xrange that gives you an iterator, and it uses parentheses instead of square brackets. Again, this is Sage specific. So what this does is it gives you back something you can iterate over. Actually, let's do it 1 comma. It works exactly like, oops, 1.5, 5. It works exactly like the square brackets one, except it doesn't include the endpoint by default. And it gives you an iterator. Okay, so those are square brackets and round brackets. They're Sage specific, and they're almost in Python, but they aren't. So I'll call it A, B, dot, 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 C, and A, comma, B, dot, 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 C. You know what, this is optional. what we have is all this Sage versus Python stuff. There's a couple of notation, I guess, notational enhancements to Python that we call it the pre-parser, but it's just something that the code is run through before it's fed to Python, which makes the code a little bit more mathematician friendly. So for example, when you type 1/3, you get the rational number 1/3 rather than 0 when you're using Sage. And these things, this notation for making a list or an iterator, this is another example of that sort of pre-parser. Yes?
So how does comparison work if you're using rational like if 5 equals 1/3?
Comparison, it just compares the rational numbers as you would expect. I mean, like 1/3 equals 2/6. It just reduces them to lowest terms. And under the hood, when you create a rational number, it creates an object in the MPIR library. So it's a high-performance library for multi-precision integers and rationals, which is very good at doing things with numbers with maybe 1 million digits, etc. Has lots of 20 years of really hard development behind it. It's a C library that's been developed by many people. It's also known, it's a fork of GMP, the new multi-precision library. Oops. Okay, so now, are we doing on time? Good. Okay, now functions. All right, so functions, the notation, it's kind of nice because it looks a lot like if and while and so on. It's just def. Then you give the name of the function, then you give the inputs, the arguments, and then a colon. And then you indent and give all the content of the function, the body of the function. And you can also have return statements optionally. If you don't give a return statement and the function just ends, then it returns none. None is a certain type of object in Python. There's exactly one of them. It's called none. It doesn't look very interesting. Its print representation is completely empty. I just printed none out. You didn't see anything. But variables, like you can set x equal to none, and now x is the variable is none. There's it's just one unique object that serves various purposes. It has a type, which is none type, and every function, you're guaranteed any function always returns something, namely potentially none. So this is kind of nice because you don't have to have, like in certain languages you have procedures versus functions, where procedures don't return anything and functions do, and they're completely different sorts of objects. That's kind of silly. In Python, everything is a function, every function, the only type of way of wrapping code is in a function, and all functions return something. There's no notion of procedure, so it's just completely unnecessary. Okay, and now the other issue with functions is you give the variables that are the input. There's some you can give by their position, and then these are keyword arguments which you can specify, as you'll see when I call the function below, by just giving their name equals something. And you can call them in any order, which is nice. They also have a default value if you don't specify them. All right, so let's do an example of that same function. So I'm just going to evaluate this and define the function. All right, and let's plug in 1, 2, 3. All this function does is print all of its inputs and then return the sum of the inputs. So it prints 1, 2, 3, and then the default values, 2 and 1/2, and then it returns 6, which is the sum of 1, 2, and 3. So it's a very simple function. Here's one where you get an error. If you just do f of 1, 2, you get an error because you must provide all of the positional inputs to a function. This is different than, for example, JavaScript, where if you leave off some of the inputs, they're just set to undefined, and the function gets called no problem. So you have to provide all of them, otherwise it's a syntax or a type error. Yes?
So you can skip A, B, C, and stuff, but you've got to give C.
Exactly. Anyone where it has a default value, you can skip it, and it gets that default value. But you must give all the positional arguments. By the way, there's some major subtlety to the default value. What? Oh,
I mean, isn't it only, is it like in phase two, you only use once? Like if you don't, like so if you don't, if it's a default value.
Yeah.
And then you call it again.
Yep.
Then the default value won't actually be the default value, it will be.
sort of. So the subtlety is that stuff gets set equal to say the list 1, 2 right here, and that happens once right when the function's defined. If you were to then change stuff somehow inside of this function, next time you call it, stuff is then that new value. So you have to watch out. And by that I don't mean setting stuff equal to something else. I mean modifying stuff. So for example, if you do stuff.append x plus y plus z, then you've modified that list in place. So watch what happens. The first time I call it, just like before. Now I'll call it again. Kind of unbearable using the screencast program. In any case, I'll call it again, and see, it's 1, 2, 6. What happened was the list stuff with entries 1, 2 was made when the code was first evaluated. That's the default value. You now modify that list in any way from anywhere in the program, and don't give stuff as an input, then it'll use that default value, in which case at this point it's now 1, 2, 6. Okay? So it's a subtlety you have to watch out for, because it's not that every single time you call a function it doesn't reevaluate this code. It just does it once. I think that's what you're asking about.
Yeah.
Because it's a gotcha that can be confusing.
And is the best way to deal with that just like if
Yeah.
check if it's
Yep.
been
The standard way of dealing with this problem, if you are writing code that would be potentially modifying this list inside the code, is to write stuff equals none, and then inside of the function you go, if stuff is none, then set stuff equal to 1, 2. So I'll just show you how that works. Copy. So here's the fix. So you write stuff equals none. None is kind of the most, you're not going to waste anything if you use none as a value for a variable. And then right here you'll just write if stuff is none, then and this way it'll reevaluate the 1, 2, or you might have, well anyways, that'll work. So this is a better version of the function f. And this one you can then call twice, and it won't have any weird side effects each time you call it. Okay, so notice that, oh, what the heck? Oops, okay, thank you. Yeah, okay, so that works. All right, so that's kind of the standard trick there. Another thing to notice about functions in Python is you don't declare the type of the input. This is different than Java or C or certain other languages, where you say that one of the variables is an int, another variable is a char star, something like that. You don't do that at all here. Probably the notation in Python, if you did do it, would be like this. You would say variable name colon and then some type, and then it would force it would maybe give it an error or coerce or convert into that type. In Magma, that's in fact what you do. You have this notation. It gives you an error if the thing doesn't match. And surprisingly, in Python 3, this notation in fact works. You can write this notation. It doesn't do anything at all though. It's just completely ignored. Yes?
But internally it's faster if you just declare the type in Python.
Well, you can't. There's no notion of declaring the type of a variable in Python. Wait, what was your question exactly?
I mean, I've just come across that internally in Python, you compile it as efficient if you declare the type in
In what Python?
in that compile.
In Python. Or
Yeah.
yeah, in Python, which we'll get to in about a week, then you can get massive, easily like a factor of 100 for certain types of problems, speedups by declaring types. But what Python is it takes Python code and it converts it to C code. It compiles that C code with whatever compiler you have on your computer, and then creates a dynamic link library from, or a shared object library from that C code, and then imports that library into your running Python process. And there you're allowed to declare data types. You can declare any standard C data type, for example. And I will show you all about how to use Cython. But by the way, so Python 3 does have these type declarations. I didn't know that until about a month ago. It doesn't do anything. It doesn't stop you from using them. Apparently, it does maybe do something regarding decorating. So the function G has extra meta information associated with it involving these types. So maybe you could write some additional tool that would then use them. But by default, it doesn't actually do anything. Okay. So, I mean, this is a pro and a con of Python, the way types or lack, the way types work or don't work. The fact that any variable, you can just change what type it has, so to speak, at any moment. On the one hand, makes code often very easy to write, but it means that some code that could be very, very fast is not very fast when you write it in Python. So the way to address this is to, in many cases, rewrite it in Cython, which is a lot like Python, but much faster. Or to use code that other people have written in C, like NumPy, to write your code in such a way that it doesn't, I mean, basically with NumPy, what they do is they provide a whole bunch of data structures where everything in the data structure is a float or an int or something, and then all the operations with objects of that data structure are highly, highly optimized. Okay, so now make some remarks. Oh, wait, I wanted to tell you about locals. So when you call a function, inside of, well, actually in any place in Python, but particularly inside of a function, there's another function called locals, which will return the local variables inside of that function as a dictionary. It's, what you get is each of the local variables inside the function, that's the key of the dictionary, and then the value is the corresponding value. So this can be handy because you can see exactly what just got defined when we called the function. That's what I'm doing here. One thing to watch out for with locals, this is a dictionary, but you can't change it. It's impossible to change the locals dictionary. So you might think of some clever code that you might want to write that would involve modifying this dictionary, but that's not allowed in Python. Okay, so now scoping, since I'm really trying to tell you all the subtleties that you're probably not going to see in the Codecademy stuff, I want to point out that the way scoping works in Python is a little bit weird. So there's, basically it's not the way that it is in most other modern programming languages, such as JavaScript, Perl, Ruby, Scheme, Smalltalk, C, C#, etc. in modern times. And what I mean by this is you can define a function, and then inside of that function you can define another function, like really right inside of the first function. And then inside of that function you can define yet another function. So you can have nested functions. When Guido van Rossum was first implementing Python in the early 90s, he modeled it very much on the C programming language, where nested functions are not allowed. You have two scopes. You have just like the file scope and the scope inside of a function. But there's no notion of nested functions there. And so basically that's how Python scoping works. You have a global scope, and then you have a scope inside of your function. And then he did a little bit of work to make it so at least stuff inside of the function can access the global scope. But if you, in Python, if you define some, so you have kind of your whole file that's global, you define a function, and then inside of that function you define another function, and then there you define another function, and maybe right here you have some variable, and maybe here you have another variable with the same name. From here you're going to have a lot of difficulty saying I want access to this variable or I want access to that variable. It just doesn't, there's no way in the language to do anything but get access to A in here or in the global scope. So it's just a little bit annoying, and it's something to be aware of, that the scoping rules are a bit different. Yes?
Yeah, so when you speak of functions inside functions, do you have closures, which is
Yes. Yes.
Well,
Well, I mean, they don't have to be anonymous. So you definitely have closures in Python, which is almost the same thing as a nested function, because it's some code with variables that have the same scope. But the thing is, in Python, you can't, anonymous functions have to be one line long, and they have to be an expression. It's kind of, there's really no good notion of anonymous functions in Python. But
Miscomprehension kind of version?
I don't think so. I wish it were, but it isn't.
And it's kind of get put in the code, so.
Yeah. But I mean, basically, nested functions are the closest you get to closures in Python, as far as I'm concerned. But here's a good example that illustrates what I just wrote over here. So we define a global variable 5, or a is 5, and then you define a function, and then you make an a, and you set a equal to 7. This a is not that a. This has no impact whatever on the a in the global scope. If you want this assignment to impact the global scope, you have to say global space a, and then suddenly a is then the a in the global scope. So it is possible. But anyways, you have this a which is equal to 7, and then inside of G, your options are, you just start using a, then you'll be reading this value. You could say global a, and then you can affect this value. But there's no way to just change that value. So it's kind of weird and annoying. But and there are ways to get around the way scoping works by writing your code using classes, and then giving classes as input to other things. Basically, there are the certain kind of patterns and just approaches to writing code that you might use in other languages, like JavaScript, for example, just don't work well in Python. So just watch out for that. You can't just directly map your sort of programming problem-solving strategy over. There's always you can do anything in Python that you need to do. You just may have to do it differently. All right, and if you want to read all about this scoping issue, there's a beautifully written webpage called PEP 3104, which just explains the historical motivation for why things are the way they are, and what the situation is now, and it gives links to discussions, etc. A nice thing, though, is that really the scoping model is really simple in a sense. It's just your variable is either global or local, and in a way that may make things easier to understand when you're reading code. Okay, here's another thing that we may have to wait until the beginning next time to talk in detail about, because it takes, I think, more than 2 or 3 minutes. Just to foreshadow slightly, though, Python actually has a really nice system for specifying functions that take a variable number of arguments, both positional or keyword arguments, and this gets used an enormous amount all over the place in Python programming. And also, it makes it very easy to pass in kind of variable number of arguments to another function. So like if you have a list or a tuple, and you want the entries in that list to be positionally placed as the inputs to another function, all you do is do, another function is called f, you do f star v, where v is the list. In other words, it's very, very natural and easy to do. Certain things that you could easily find showstoppers if you don't know about it. So we'll start at the beginning next time with this, but it's really, really important to understand this because it makes many things possible using Python that would be just totally impossible otherwise. So that's what we'll start with at the very beginning next time. And then we'll start talking about classes.
How do I open the Sage worksheets that are on the web?
It is impossible until I release the program that makes it possible to open them, which I will do hopefully Monday. But it's really hard. I've been working on it for like 8 months. Right now they're JSON objects, so you can open them and look at them, but yeah, it's just not quite possible yet. Sorry. Yes, let me just stop this.
I sent you an email about an ad code yesterday.
Okay.